will continue with our water tanks. We discussed that the water within the tank can be considered as two separate masses, Mi and Mc. Mi is rigidly connected, impulsive mass, it is rigidly connected to the tank, and the convective mass Mc can be connected through a spring having stiffness Kc or two springs having stiffness Kc by 2. Okay. The height of this mass Hi and convective mass Hc, all these parameters we have written. Okay, I have given you the charts and expressions to compute this. Okay. Then in case of overhead water tank, this is on ground. We have considered that this is our Mi plus Ms. The stiffness is coming from the staging. The stiffness of the staging you can calculate in the same manner as for a frame. Okay, so we discussed that how to calculate the stiffness of a frame in a building. Same method we can use to calculate the stiffness of the staging. And another mass Mc connected with the stiffness Kc. Okay. We also discussed how to calculate the period Ti and Tc. Up to this point, we have discussed in the last class. Any doubt up to this point? We can discuss.
Sir,
Yes.
we are calculating for impulsive period. This Q is in per meter square.
Yes.
And when we are calculating delta, it will come into per meter.
Right.
Because this Q is in
Because Q is on unit strip width. So T also, okay, here I, when you are calculating I, the width will also be 1. So that will cancel out. Finally displacement will be per meter. So sorry, in meter. So delta you will get will be in meter. Because force also you are considering on 1 meter width, and moment of inertia I also you are calculating for 1 meter strip. Unit width is. Any other doubt? Yes, one. Sorry, this is plan. So this strip is of high end. No, it is not important. So we are assuming that whole of the wall will move in the same period. So we have taken wall maybe of any width. We are just considering 1 meter width. We are calculating period of that. Same period will be of the whole wall. That's the idea. What is the error here? When we are considering unit width, what we are not considering? The support from the perpendicular walls. Actually, these walls, in case of a rectangular tank, we are considering a unit width here, and on this we are considering this Q. In the elevation, it is like this. This Q okay, or rather Q into H. we are applying here. Okay, here this is pressure. So we are considering this strip. We are ignoring the support from the adjacent portion of the wall, but we can see that here actually when it will be deforming, it will not be deforming freely, rather it will deform like this. At the corner you will get support from it. This has been ignored. Okay, real deformation will be like this. In the center the deformation will be more. Near the corner the deformation will be less, because these walls will act in plane action, like we do in case of masonry walls. We have in plane and out of plane action. So those walls which are parallel to the earthquake direction, those will act as in plane, and those will support these out of plane walls there. But if this dimension is sufficiently large, the effect of these cross walls can be ignored. Okay, so we are considering just one strip here and assuming that whole of the wall is moving with the same period. Any other question? So that we can calculate the design ratio design force, again due to convective and impulsive, both the components, it will be different. So due to impulsive component, it will be AHI into MI into E. And what will be AHI? Z by 2 into I by R into SA by G, okay, at Ti, impulsive. So you need to know I and R. I and R are again given in code IS 1893 part 2. So please look at this table 2 and table 1 and 2. So table 1 gives you the importance factor. So you look at this importance factor 1 and 2. What do you understand from this? Table 1, importance factor for category 1, 1.5 and category 2, 1.0. So what are these two categories? On what basis? How do we define importance of any structure? What is the general principle of defining importance? Like buildings also, we have defined importance. So how do we define importance of a structure? What is the criteria? There are two criteria. One criteria is the hazard, any secondary hazard caused by failure of that structure. And second criteria is post-earthquake importance. So we define importance based on these two principles. If it will have any secondary hazard, so in case of water tanks or tanks, liquid retaining tanks, do you think any hazard can be caused? If the tank fails, can there be any hazard? If water tank fails, what would be the hazard? secondary hazard.
Water tank is near the building.
It can fall on the building and it will damage them. Okay. So that can happen with any structure. So we are designing them not to collapse. But it may fail, it may damage, liquid may flow. So do you think any hazardous situation can happen?
Water scarcity.
Water scarcity, so that is post-earthquake requirement. So one thing is post-earthquake requirement. So some of the water tanks, without those we can work for few weeks. Some of the water tanks we can't work without them. So that is last statement of that either required for firefighting or earthquake importance, post-earthquake importance. That is one. But tanks, not the water tanks, but some of the liquid storing tanks can cause secondary hazards also. For example, if the tank is storing, let us say, petrol, and the tank fails, there is fire hazard. If it is storing some chemical which may be dangerous, so that also, that type of tanks are not governed by this code. Those are governed by IS 1893 part 4, that is industrial structure. There the importance factor can be more than even 1.5. The tanks, if you read carefully, the tanks which it is talking about is those liquids which have low inflammability. So inflammability may be there. Water is not inflammable, but there may be some other liquids which have low inflammability, but those can catch fire. Okay, so there you have to take importance factor of 1.5. But other chemicals which are hazardous or are inflammable, those can catch fire after earthquake. Those will be governed by IS 1893 part 4. Analysis will remain same, but their importance factor will be obtained from IS 1893 part 4. Okay, and other tanks which are neither hazardous nor very important, for them you can take importance factor equal to 1. Okay. Now look at this table 2, where response reduction factor R is defined for different types of tanks. So look at this response reduction factor value. What type of tanks you have commonly seen? Generally in the campus also, when you go around, you see some overhead water tanks. So what type of tanks you will put them in which category? And you can see that these tanks, the response reduction factor for tanks is given based on their support, staging or shaft. So what type of staging and shaft those are supported on, that will decide. Then table 3 gives about the ground supported tanks. So which is having higher value of R, overhead tank or ground supported tank, or underground tanks. There are underground tanks also. So look at these three: above ground, underground and overhead. Which is having larger value of R? Underground? Why the above ground tanks are having less value of R as compared to overhead tanks? Overhead tanks can have response reduction factor up to 4. Whereas above ground tanks have response reduction factor maximum up to 3. And underground also has response reduction factor 4. Why so? Not 2.5. If you look at RC SAP with reinforcement in 2 curtains in both directions and with this different openings and bracing, that means whatever details, tactile detailing we are doing for shear wall, similar type of tactile detailing we do for RCC SAP also. Then response reduction factor is 4. This is what's on it. This is what's on it. This is some intermediate document which was used for right side. See, IS 1993 Part 2 2014. Otherwise, we can open here. अच्छा वो लोडेड नहीं है? So why do you think that overhead water tank has larger value of R? On what the value of R depends? On what characteristic of the structure? R depends. Ductility or inelastic energy dissipation. So why energy dissipation will be more in case of overhead water tanks than the tank supported on ground? If there is a tank supported on ground, where the plastic hinges will form? And if it is overhead water tank, where the plastic hinges will form? What do you think? In the two cases, how the energy dissipation will take place?
In case of overhead tank, plastic hinge will form at the bottom of that stacking.
Why at the bottom? Why not in between?
Because we will make a strong column of between.
Yeah. So first it will form in void beam or column?
First it will form in beam.
So why you are not saying beam? Why you are saying at the bottom of the column?
But the ductility we want, it is getting from the column hinge.
Why?
Because when the structure will go in elastic range, delta we will get in with theta y into h height of that tank.
But in case of a frame, theta y depends on what? You remember the formula for theta y? Does it depend on the column or it depends on beam? It depends on beam. So energy dissipation will take place on the beam and collapse will occur finally when the hinges will form. But before that, the beam should yield. Okay? And beams will dissipate the energy. If the tank is on staging, the tank can be on staging as well. Then where the hinges will form?
Hello, at the bottom of the column.
So the cross section here is like this, where the hinge will form in this cross section.
Outside, outer building.
Outer very out. Draw.
Because due to bending, stress will be maximum at outer
So
building.
where the hinge will form? How the plastic hinge will form? Where the hinge will happen?
Heating will start from each point at the outer building. So stress will be.
So which portion will yield? Can you draw that portion? Can you mark that portion which is going to yield?
If earthquake is coming on this side, like this, then this half portion will be, because tension will be on this side. And earthquake will change the direction. This portion will start.
And at which location along the height this will happen? So it is natural that it will occur in the base. So this portion at the base, this is going to be, and this section, because earthquake is reversible, so this whole section will yield. Part will yield when earthquake is towards right, part will yield when earthquake is towards left, and earthquake is coming in all the directions. The whole section will yield. And if this section is yielding, you want adequate ductility, what should you do to achieve adequate ductility? Confinement. How you are going to provide confinement in this section? Then reinforcement. Code says that the reinforcement is to be provided in 2 curtains. So longitudinal reinforcement is provided like this. In hollow circular shaft. How you will provide the horizontal reinforcement? This is the longitudinal reinforcement, vertical reinforcement. How you will provide the horizontal reinforcement? Is it difficult?
Yes.
No. So you will provide one strut here, outside this, and you will anchor it here. Another strut you will provide inside the inside layer of reinforcement. And you will anchor this. So this is the horizontal reinforcement. So horizontal and vertical reinforcement both will be provided in 2 layers. Is it adequate for confinement? Will you get confinement from there? You recall when we were talking about columns, we discussed that a circular column with circular stirrups has the best confinement. Okay, because whole of this perimeter of the transverse reinforcement is causing confinement. It is effective. What will happen when this is hollow? Suppose this inner reinforcement was not there. Just I make a hollow here. What do you think about this confinement? What will happen to the confinement? Will you still get confinement or concrete? Why not?
Because there should be a material which can resist, can provide the reaction.
Why you need that material?
If you are compressing it from outside,
Mm-hmm.
then it will try to compress it. But you have this much thin piece, whatever the thickness is that.
Mm.
So this one the material you have. So it will try to compress it. But the means this side of your concrete is hollow. It has no support. It will simply fall down. Means it's not simply fall down. It will fall down.
It will go down.
What will go?
When this portion is hollow, load is applied, that inner core of that between the two stirrups will get compressed. Outer side it has stirrups, but inner side there is no one to pull it outside. When it is compressing, there is no one to pull it inside. So there will be less contact. And if I provide,
If you have this type of reinforcement details, okay, the concrete here, on this side, the concrete when you are applying stress on the concrete in this direction, okay, it has tensile strain in both the horizontal directions. So in one direction it is confined, but in the other direction it is not confined. In other direction, on one end it is confined because of this stirrup, other end it is not confined. So what will happen? This concrete here, this will spot. This will get crushed. This is called, and this will be sudden failure. Okay, because you are compressing the steel and then it will burst due to tension. When the stress here will exceed the tensile stress, it will fail. So we will have a bursting failure into the hollow core. We will have a busted type of failure. Now suppose I have provided a reinforcement here. What will happen then? I have provided a stirrup here on the inner face also. Can we get confinement?
yes,
How?
because now this concrete want to come outside. This stirrup will provide resistance to go inside, and when this is
So
coming
what
out,
will be the behavior of this stirrup? Will it be in compression or tension?
it will be
Inner stirrup. You have a circular section subjected to compression in this side. When compression will be like this, it will try to expand.
put tension.
So the concrete will try to expand like this in both the directions. You agree? If I am applying pressure like this, the concrete will try to expand in both the directions, inside as well as outside. So what type of forces you expect in this stirrup? Inner stirrup. Inside? This type of pressure is acting. What will be the force in this ring?
inside.
Tension. If you are pulling it inside, it will have tension. Then what will happen if I have this type of pressure? Both will have tension. So what will happen in the first case? Is there only hook tension? There can't be hook compression. If the pressure is applied from outside, there will be hook compression like this. So this will be subject to hook compression, this will be subject to hook tension. Here it will try to expand, here it will try to compress, and it is made of a steel bar of 8 mm diameter. You are subjecting it to hook compression. What will happen? If you have a thin section like this and you subject it to hook compression, what is going to happen? It will buckle. Okay, it will not yield. Here, it can't buckle, it is in tension. So it will yield and it will rupture. Here it will buckle. So this inner loop cannot provide confinement because it will buckle before yielding, before developing its full strength, it will buckle. Okay, so to provide confinement, what do you think? What should we do?
We should increase the number of the longitudinal bars so that the effective length between these two loops will reduce.
But longitudinal bars are not supporting this stirrup. This stirrup is supporting the longitudinal bars. So if you are providing more longitudinal bars, those are not support. Those can't support this stirrup. So for confinement, you have to provide ties like this. So this transverse reinforcement is necessary. This reinforcement will provide you the confinement. This will not let these longitudinal, inside longitudinal bar to move. Okay, so this is going to provide you the confinement, not this stirrup. The outer stirrup will provide the confinement. Okay, if concrete was solid, then just this outer stirrup was adequate to provide the confinement. Okay, but when it is hollow, then providing another stirrup inside can't provide you the confinement. Okay, so this horizontal and vertical reinforcement if I draw the section of the ball, there will be vertical reinforcement here, vertical reinforcement here, vertical reinforcement here, vertical reinforcement here, and then there will be stirrups. These circular stirrups will also act as shear reinforcement. Sorry, horizontal stirrups will also act as shear reinforcement. So these will take care of the shear force which is occurring in this. Okay, so that shear force will be taken care of by that. But in the lower portion, you need confinement also. So in the lower portion, here you will provide these ties also. So that where it is yielding, the concrete is confined and steel rods are supported against buckling. Then only you will be able to get it. So this ductile detailing you have to provide in case of shafts. In case of staging, what ductile detailing? In case of frame staging, what type of ductile detailing you will provide to get higher value of R? As we have done in case of building. What is that? N of confinement in beam and column near the joints. Okay. What else? Other than that, what ductile detailing requirements are there in case of a building, frame building? This you should never forget. So what requirements are there in case of a building frame for ductile detailing? There has to be confinement near the joint because hinge forms there. Other than that, what?
Anchorage length.
Anchorage length.
Like LD plus 10.
So LD plus 10.5 will go here. Okay, what else? Yes, you were saying something? Labs. So you will provide a special confining reinforcement at labs also. What else?
Sigma at joint shear. We are looking joint at the beam column check for that shear.
So the joint should be checked for shear, joint shear. What else? Strong column, weak beam. So column should be stronger than the beam. What else? Something very important you are missing. That is the first step.
Grade of steel. Grade of steel.
Okay, grade of steel, but I will not mean that. Avoiding shear failure, capacity protection of shear. Shear capacity should be more than the flexion capacity. The capacity design you have to do. The beams should fail in flexion, not in shear. Okay. Similarly, column should fail in shear, not in flexion, and column should be stronger than the beams. And the strength of the joint should be more than the strength of the connecting beams and columns. These are called capacity design. Together, these are capacity design concepts. Beam should not fail in shear, column should not fail in shear, column should be stronger than the beam, and the joint should be stronger than the beam and column. Okay, these are capacity design, and rest is confinement. So other requirement is that there should be adequate confinement. So those provisions you will follow here also, then you can get the response reduction. Okay. Now where the hinges will form in case of ground supported tank? Where such hinges, where energy dissipation can take place, where those are going to occur? Let us say it is subjected to earthquake in this direction. Where the hinges will form? How the failure will take place? Where the failure will take place? Can you visualize? It is filled with water, and when it is subjected to earthquake, water pressure, hydrodynamic pressure will be applied on these walls. So what is going to happen?
Corners of the base.
Corners will be
Corners of the bases.
should be braced.
Base corners.
Braced corners. Why braced corners? What will happen at the corners?
The bending moment will be less.
So we discussed that this wall is going to bend like this. And what will happen at the corner? At the corner also there will be movement. Okay, so there will be, if you are talking in this direction, there is sagging moment here and hogging moment here. Okay, and here will be a shear force also due to this water. So corners will be subjected to large bending moment and shear force. So there will be not a hinge but a yield line. This wall will yield here. Okay. Then it becomes like simply supported when yielding occurs here. Then where will be the next yielding occur? Okay. So energy dissipation will take place through yielding of walls. Yielding of walls, you can imagine like if this is a water tank and water pressure is applied to this wall, where the yielding is going to occur? The yielding is going to occur here first. Why first here, not here? Whether it will happen in center first or at the ends first. It depends on the end conditions. Okay, so if this wall is rigid, these walls are enough rigid, then the bending moment, suppose these were fixed. So in case of a fixed beam, the fixed end moment is more than the mid-span moment. So first the yielding or the moment exceeds the capacity at the ends. Okay, so same thing will happen here if these are rigid. And then once yielding occurs here, then the bending moment diagram will change. Okay, it will behave like a simply supported for additional moment, and then the plastic hinge yielding will take place. The steel reinforcement will yield.
And shear force is coming from earthquake.
It is coming because of the water pressure acting here. The water pressure is acting perpendicular to this wall. So that water pressure from this wall is to be transferred to the cross walls. So that will act as shear force at the junction. So you have to ensure that this wall should not fail in shear. Shear capacity should be more than the fraction capacity. Okay. How you will ensure that? Generally in case of walls and slabs, we don't check for shear. Okay? Assuming that the slabs never fail in shear. But here it may be different. And suppose it is failing in shear, what will you do? Suppose it fails in shear. What will you do?
We will increase the cross-sectional area.
We will increase
The cross-sectional area.
cross-sectional area means thickness of the wall.
Thickness of the wall.
If you are increasing the thickness of the wall, what will happen to the fracture capacity? Fracture capacity will also increase. That will not help. In fact, fraction capacity will increase more rapidly. Fraction capacity is proportional to T square and shear capacity is proportional to T. So increasing thickness may not help. So what you are going to do? You have to provide shear reinforcement. How the shear reinforcement is provided in this wall? In which direction? Same as we have done in our staging. So if I draw the plan, so this is the plan. So reinforcement will be in two layers. horizontal as well as vertical, and then the shear reinforcement will be provided like at least near the joint. And so on. Okay, so near the joint you will provide shear.
Can we analyze this as taking 1 meter strip as a fixed beam? Like this top one portion 1 meter is connected.
So if you take a strip here, this strip, and you take a strip here, the behavior will be different.
Yes, change in pressure will be happen. We will design for maximum
We will design for
pressure.
maximum pressure.
And we will provide throughout the
Maximum pressure is at the bottom. You know the pressure distribution. Hydrostatic pressure increases like this, inertial pressure increases like this, and convective pressure varies like this. So where is the maximum pressure going to occur? Bottom. But in bottom, can you analyze the system?
we will provide cable section.
Why taper?
The bottom load is coming larger, so larger portion.
Yes, but at bottom it is supported also. You have to consider this strip also. And when you consider this strip, it is like cantilever. At the support, the slab is also there now. So the water pressure is more at the base, but at the base it is supported by the slab. So there is no need to increase the heat. Okay, but you can see that it becomes a complex problem for different type of pressures, and you have to perform analysis of this either using finite element method, or there is a code IS 3370. This is the code for design of water tanks. The code which we are doing, which we IS 1893 part 4, this is criteria for earthquake resistant design of water tanks. Okay, it is not design of water tanks. Design of water tanks is IS 3370, and it has 4 parts. Part 1 is general requirements. Part 2 is RCC tanks. Part 3 is pre-stress tanks. And part 4 is design tables. And design tables, again, there are different sections. Section 1 is plates. Section 2 is rectangular tanks. Section 3 is circular tanks, and there is also section 4. I do not know. Okay, so something like this. 4 parts, and so it's a huge, large code. So what we are discussing here is RCC water tanks. This code has been revised in 2021. So in 2021, limit state design has been introduced in water, in liquid retaining instruments. Before that, it was working stress design. time you are designing a water tank, you have to satisfy limit state of collapse. This will be from IS 456. Same, you will use limit state of collapse, the limit state of collapse in flexure, limit state of collapse in shear, limit state of collapse in compression. Okay. In case of water tank, what is the spatial requirement? What makes it different than other structures, design of other structures as per IS 456? In what way water tanks are different? Water tanks are different because these are subjected to most of the structures like columns. When we are designing for compression and bending. These are subjected to tension, bending and shear. Why tension? If it is circular water tank, due to internal pressure, it will be subjected to hook tension. If it is rectangular water tank, the water pressure will be acting on all the four walls uniformly. And you can see this pressure will cause tension in these walls, and this pressure will cause tension in these walls. And then these walls will be bending like this. So the walls are subjected to tension as well as bending. Okay. How to design RCC members for tension and bending? Same method as we have done. We have seen the interaction curve. We have plotted PM interaction curve. So P is not only in compression, it is also in tension. So this portion of the interaction curve will be used here. Generally, so far you have considered only axial as compressor. Here, the axial force is tensile. In presence of axial compression, what happens to shear force? You recall in IS 456, if axial force is there, what happens to the shear strength? Increases. What will happen in presence of tension? Will decrease. So the shear capacity will decrease. So the shear decreases. Shear capacity decreases. I am not covering all that. For that you have to refer to IS 3370. Okay. For design, what we are limiting here is up to calculation of forces in ground supported tank and overhead tanks. What will happen in case of underground tanks? Anything additional? You see, suppose I have a tank which is, let us say, partly embedded into ground. And it is subject to shape. What are the different failure modes?
It will slide down.
It can slide. Where? In which direction?
Multiple direction.
So how to check its stability against sliding?
Shear, whatever the shear force coming, that is given, and the shear resistance power.
So you have to calculate the total shear V, okay, and then the friction which will be coming from here, plus the passive pressure which will be coming from here, minus the active earth pressure which will be coming from this side. And this will be dynamic passive earth pressure, which is smaller than static passive earth pressure. Due to earthquake, the passive earth pressure will reduce, whereas the dynamic active earth pressure is going to increase. Now, I have a fully underground water tank. What will be the most critical condition for this water tank? The most critical condition for this water tank will be when this is empty. Its design will be governed not by water pressure but the soil pressure. When it is empty, when it is full, there will be water pressure from this side and soil pressure from outside. So you can see these will counterbalance. But when tank is empty, and tank can be empty, at that time this inner pressure will not be there. And only this soil pressure will be there. That will be the most critical condition for underground water when it is empty. And which type of soil pressure this will be? Active or passive? In normal condition, it will not move. It is not moving. Okay. So it will be neither active nor passive. It will be pressure at rest. Soil pressure at rest. When there is no movement. Okay. Now which one is higher? Soil pressure at rest, active earth pressure or passive earth pressure? Can you arrange these? Passive is highest, then rest or active? You were saying rest. And then active. Okay. Why active is lower than the earth pressure at rest? So when the structure is at rest, the pressure will be higher. When it starts moving away from the soil, we will have active earth pressure, which will be lower. If it starts moving towards the soil, then we will have passive pressure. That will be higher than pressure at rest. Okay. And the code says that here you can take, actually it is not exactly at rest because you will excavate and then you will fill up. So some disturbance will be there. So we should take pressure as average at rest and active. Earth pressure. Let's take average of that. Active earth pressure is slightly less. Suppose our pressure is more, then the tank will start moving, and if it moves a little bit, the pressure will break. So it takes to take average of the two. That is allowed by the code.
So we should consider rest plus passive because we will change of earthquake direction.
Passive is very high, okay, and passive will come when you are or the earthquake is pushing against the soil. Normally it will not get pushed against the earthquake. So passive pressure will not generate. Passive pressure will generate only in this case when the tank tries to slide. When tank is fully embedded, it cannot slide. So the pressure you will get will be at rest or between active and at rest.
So
Passive pressure generally, so what happens when the structure moves away from the soil? This is our structure, maybe tank or anything. When it tries to move away, the soil here will fail, and the friction which will develop on the soil here that will reduce the pressure at the bottom. On the other hand, the soil is here and our structure moves in this direction. Then it will push. Here the soil is moving in this direction. Here the soil has to be pushed like this. So what will happen? The resistance will be opposite. Okay. So this is the resistance. So here this pressure is going to increase. So in passive pressure, the soil is resisting its movement. Okay. We are moving soil against its pressure. And here the pressure is reducing the movement, or the soil friction is reducing the movement. Okay. So that is reducing the pressure. So this will be additional aspect when we are talking about underground water tanks. So let's see how we will calculate these forces, because in this course we are limiting ourselves to calculation of earthquake forces. Yes.
This active and passive is decided based on the movement of the tank overall.
Right.
But if my tank is rigid one, having large mass, and due to earthquake, soil is coming towards the tank, then which will I will consider.
So whether soil is coming or tank is coming, it will depend on what is the relative motion. Is tank going away from the soil or tank is moving towards the soil? Suppose soil moves towards the tank due to any reason. Tank is static. So what does that mean? It means that the tank is being moved towards the soil. So it will be passive pressure. Where this situation happens? Can you imagine? Where tank is static or structure is static but soil starts moving. Can you think of that situation? When this situation happens?
On soil, new construction will happen.
When?
On soil, new construction will happen. The
No.
soil will on.
I couldn't get.
Where the compaction is not done properly.
This happens during liquefaction. Okay, there is a phenomena called lateral spreading. So, suppose you have a foundation, generally a bridge foundation. Here or a pipe you may have. This is the surface. There is a rigid layer at the top, then there is a flexible layer, and then here are rigid layers, rock or rigid soil. This is the pipe. This is liquefiable soil. And suppose there is a slope in these layers. These layers are somewhat sloping. And when this layer liquefies, it becomes like liquid. What will happen? Due to the slope, this will start moving. This is supported over the liquefiable soil, so this layer will also move along with this. This is called lateral spread. This pile or pier is supported on this soil. This soil is rigid. This will not move. The soil above is moving. So what will happen here? When the soil is moving. So soil is moving, the structure is static. So in that case, the pressure which will be acting here, that will be equal to the passive pressure. The lateral pressure which will be applied on this pier or pile is lateral earth pressure, lateral passive earth pressure. And this pressure is very huge. Failures during liquefaction occurs mainly due to this phenomenon. If liquefaction is occurring at a site which is having a little slope, then it is very dangerous, what we call lateral spread. And bridges are mostly constructed in this type of situation. Near the river, water table is high, chances of liquefaction are there, and it is sloping also towards river. So after liquefaction, the soil will start moving towards the river. Okay, and the bridge pier has to register. So bridge pier or the pile or well, whatever foundation we are providing, that has to resist this earth pressure. So this situation occurs. You ask, so I explained. So in some places, this situation is also occurring where soil is moving, structure is standing. Okay, but the net relative movement is such that the structure is moving towards the soil. So there the passive pressure will die. Any other question? Here passive active pressure. That is in a static condition. That is only in static condition. This situation which I am showing here, this is in a static condition, not in earthquake. Earthquake, the situation will be like this when the movement will start. So when you are considering the static case, then you have to consider the pressure as average of at rest and active. In case of earthquake, on one side it will be passive, other side it will be active.
So,
Yes.
for design of any structure, we consider living state of collapse and living state of observation. What does it mean, living state of collapse? Collapse means what?
Collapse means that the structure has failed. For example, when a water tank will collapse, either the staging fails, water tank will come down, or suppose the staging is standing, that what the water tank walls, those get ruptured, those heave and water comes out. That is limit state of collapse.
Okay, whenever the limit comes, we are using the maximum safety. We are using permissible stresses, the fire or something factors. And how it can fail? It doesn't collapse. We are making.
Suppose it will fail only if you make a mistake in your calculation. Otherwise, it should not fail. So, or you have considered the properties in your design which are not there at the site. To take care of those only we use the factor of safety. But even then sometimes you may make an error which is larger than the factor of safety. If no error is made, then it will not fail. But if you make an error, okay, in calculation of the forces or in construction, then that error is more than the factor of safety which you have considered, then it will fail. Or during earthquake, where there is no factor of safety. So in case of earthquake, there is no factor of safety. Earthquake force will be much larger. In fact, even in the water tank, we are designing for 1/4 of dB. Actually, it will become MC. And even if you consider overstrength factor of 2, it will be only 1/4. The strength will be only 1/4 of the force which will come under MC. Then it will fail. Okay. So failure is possible even after considering these factors of safety. We have to identify those modes in which failure is probable, and then we should ensure that strength is sufficiently higher than the demand in those modes. That is our limit state of collapse. What is limit state of serviceability? In case of water tanks, limit state of serviceability in case of water tanks is related to cracking. Okay, suppose you have provided enough reinforcement and it is safe against collapse, but it may so happen that the concrete may crack under service load, and when the concrete cracks, the water leakage will happen. Okay, so certain crack width is allowed up to 0.2 millimeter. Crack width is allowed. But if the crack is more than 0.2 millimeter, then water leakage will start. Okay, so that is not done. So under serviceability load conditions, you will check for the cracking. And the water tank codes include earthquake loads also in serviceability condition. Only thing is that the load factor is 0.3. So if you look at IS 3370, it provides you the different load combinations for which water tanks are to be designed. Okay. So for limit state of collapse, the load factor for earthquake is 1.4. For limit state of serviceability, the load factor for earthquake load is 0.2. Okay. So there we will be checking cracking. Have you ever checked cracking? Do you know how to check cracking? It is available in IS 456. Look it there. It is also available in IS 3370. There is an annexure. So it gives the cracking for immature concrete as well as cracking for mature concrete. Okay. In the green state also, due to creep and shrinkage, it will crack. So that crack width also you can calculate, which is going to occur during setting of the concrete. Sometimes you have seen in the buildings, soon after the plaster is done, as the plaster starts maturing, okay, drying, you get cracks. So those are due to shrinkage. Any cement-based material is going to shrink. So when the water evaporates, it is going to shrink. So concrete is also going to shrink, and it is a circular tank. Its diameter cannot change, whereas the concrete is shrinking. So what will happen? There will be cracks. So that crack width also you have to control, and then during the service life and during earthquake, there can be cracking. A major earthquake is occurring, you are not expecting that your water tank will be able to retain water. Leakage will occur, and later on, when earthquake is gone, you will repair. That's a different case. But smaller earthquake, what we call submersibility level earthquake, which 3370 defines as 0.3 times the dB. Okay. For those, you have to ensure that tracking should be within limits. So that will be taken care of by the limit state of submersibility. So our job now remains, if you understand IS 43456 and IS 3370, those are now designed as earthquake engineers. The additional thing which we are giving is the forces due to earthquake. So that's what we were doing from where we have deviated. So we were calculating the earthquake forces So we have calculated AHI. Using AHI, we can calculate VI. Okay. Can you calculate MI? Moment due to impulsive component. That will be VI into HI is spark, not HI. Because overturning at base also should be plus. Similarly, you can calculate AHC. AHC will be Z by 2 into I by R into SA by G at TC into a damping factor. I told you that in convective mode, the damping is very small. So, into a factor which I am calling beta. So, beta is function of psi c and psi c is 0.5%. So, convective damping is only 5%, sorry 0.5%, whereas impulsive damping is same as that of the structure. So, for RCC tanks it is 5%, for steel tanks it is 2%. Let us check where the diameter is given. Okay, you can look at page 7, 4.4. Diameter. Have a look at this 4.4. Same thing what I have written on the board. It is repeating. In case of convective component, you will have damping only 0.5%. Whereas in impulsive, it will be 2% of critical for steel and 5% for concrete and masonry tanks. So the response spectrum given in the code is for 5% damping. So for RC and masonry you can use that response spectrum directly. For other damping, what you have to do? Either you can use that R-Zyme which we discussed, or in IS 8093 part 4 a table is given for multiplication factors which are close to those which you will get from the formula of R-Zyme which I have given you. So close to that, yes. Part 2 also there will be. So they have given just the factor for 2% and 0.5%. They have given the full table. but they have given the value of this beta xi c. Okay, so beta xi c for 0.5% it is 1.75, so 75% more spectral acceleration, and for 2% still it is 1.4. So due to this, on the wall, if I am calculating the shear force V, so this shear force V on the wall, this will be due to the self weight. Or self inertia. Self inertia of wall, let me call it VW. How you will calculate VW? Mass of the wall into AH, I into G. Okay? Due to its own weight, there will be a force. Then there will be, due to impulsive pressure of water. Let me call this VI. How much will be VI? MI into AHI into keep in mind, if you are calculating it for unit strip rate, you have to consider MI also corresponding to that unit strip rate. This you have to keep in mind. If you are calculating for the full wall, then you will consider full MI. Then there is shear force due to convective. Pressure of water. Let me call it VC. How much will be that? MC into AHC into G. And there will be V that is due to vertical component vertical component of it. How much will be due to vertical component of earthquake? Two-thirds of VV, two-thirds of what? VS, VW, what? Two-thirds of what? Two-thirds of
each one. VW, VI.
It's not like that. I told you what is the role of vertical component of earthquake, what it is doing. In a way, it is increasing the acceleration due to gravity. So the pressure will increase. That you have to consider in shear force. So this VV will be rho into AH into H. Okay, that is the pressure at the base. I am calculating the total force. So into H by 2, sorry, not AH, AV, the vertical component. And what will be this AV? 2/3 of Z by 2 into I by R into SA by G at 0.3 second. Because in vertical direction, all the structures are rigid. So for rigid structure, we are considering the period as 0.3 second. That means peak 2.5. So actually this is 2.5. So that will give you AV. AV will increase the pressure, triangular pressure. That total pressure you have to calculate. That will give you AV, and VV will be this. Okay. Now, how to combine these? Can we add them together? How will you find it like that? One is because of the vertical earthquake, another one is because of the horizontal.
Square root of this one. VV plus VH.
So how we are going to combine this? You can see that VW and VI, these are occurring in phase. These are vibrating with the same phase. So these you can add directly. Okay? VC is out of phase with a different. So this you will do with the square. What about VV? That is again out of phase, and VV you will consider only 30%. So the design base shear will be, or design shear in the wall will be V wall plus VI square plus VC square plus VV square multiplied by 0.3. Okay, so on the wall of a ground supported tank, the shear in the wall you can calculate like this. How you will calculate moment? These shear forces are acting at the corresponding heights, corresponding points of application. Where is VW acting? So let me write down this also as MW plus MI whole square plus MC whole square plus 0.3 MV. And what is MW? VW into H by 2. MI VI into HI, and VC is equal to, sorry, MC is equal to VC into HC, and MV is equal to how much? VB into where is the resultant of the pressure due to vertical component of earthquake is acting. Center of base. Center of base, what it will do with wall? What has to do with wall? How is the pressure on the wall acting? Due to vertical component of earthquake, how the pressure on this wall is varying? It is very linearly. Didn't we discuss that yesterday? So it is very linearly as the static pressure. Where is the resultant of that acting? Where?
1/3 height of this.
Similarly, in case of an overhead water tank, if I want to calculate the moment acting at the base, let us say this is HS, height of staging or height of shaft. This is my MD. So how I will calculate MD? The square root of MS plus ML square plus MC. No MV. Why not? In moment, there is no MV due to vertical component of earthquake. Why not? Because the pressure which will be applied on the left side will counterbalance by the pressure applied on the right hand side. So due to static force or vertical component of the earthquake, the water pressure will be applied in on both the walls in opposite direction. So it will counterbalance. If you are considering individual wall, then this will come. But when we are considering overturning of the structure as a whole, then it is not going to come. So here it will not be there. Can you tell me how much is MS? MS is equal to Vs, that of the structure, into the height, wherever the CG of the water tank is. I am calling that HCG. Vs into HCG. MI VI into HS plus HI star. Because this is HS and this is HI, wherever MI is active. Okay? And because we are considering overturning, so it will be HI star, not HI. MC VC into HS plus HC star. How much is Vs? That is AHI into mass of the structure. What is mass of the structure? Mass of the tank plus some portion of this staging you can lump in. How much? 1/3 maybe or half. So half of this staging plus water tank you lump in. That is your MS, and it will be lumped at the CG of this water tank. And it will also include the weight of water. No, it won't include weight of water, because the effect of the weight of water we are considering in VI and VC. So VI and VC are actually the inertia force acting on water. So the water weight will not be there. It will be only the empty structure weight. When water tank is empty, at that time, what is the weight of structure? That is MS. Okay, VI, that will be AHI into MI into G. And VC will be AHC into MC. Okay, so that will give you the moment. Using this, you can design your skill.
So in last case, L is equal to VV into H by 3. This VV we are considering
You do vertical component of it.
a vertical component. That vertical component will play a role in this course. Whatever the course actually play.
Yes.
Then
It will not cause any overturning.
Ah.
It is acting in both the directions. So there will not be any overturning.
so where is this when we go?
This is in case of force calculated in the wall, or the moment calculated in the wall here. When you are considering this, then this earthquake force, this pressure will also cause moment here, because this is not going to counterbalance this. It will cause here also, it will cause here also. So when you are calculating the moment in the wall, then this pressure component will be considered. But when you are considering moment at the base, then this will counterbalance. This will cancel out.
The question is that when vertical forces are having, then how this horizontal force will change?
Because when, suppose you are standing in lift and lift starts moving, what do you feel? You feel your weight has increased. Similar way, when earthquake will come, okay, what the water will feel? Water will feel that its weight has increased according to how much? Equal to m into acceleration.
Yes.
So that weight of water will increase, and when the weight of water is increasing, what will happen to the pressure? The little pressure will also increase. That pressure we have calculated. Distribution of that pressure will be same as under G, because it is similar to G. It is only causing an increase in G or decrease in G if you are considering downward or upward. Okay. Last thing, this is about overall, but in case of water tank, Suppose you are interested in getting this distribution. You want to plot this distribution. And this distribution. You want to plot. If I plot on a circular tank, then this distribution as we discussed earlier, suppose you want to do finite element analysis. If you are doing simple analysis, I have given you the formula. But suppose you want to do finite element analysis of this, then you need to apply pressure. You have to apply pressure at the wall, you have to apply pressure at the base. So you need to know the distribution of the pressure. How to get that distribution? So that for that you can look at this section 4.9. So look at this section 4.9. It is giving us the distribution of the pressure along height as well as along perimeter. Along perimeter, it defines in terms of an angle phi. So it is varying with phi. Okay? And along the height, it is representing in terms of y by h. So this is y and this is h. So for example, PIW acting on the wall is QIW, and this QIW is function of y into AHI, which is same as we discussed, into rho GH cos phi. So phi is this angle, rho GH, you understand, and this QIW, this is function of y only. So this is 0.866 1 minus y by h square into 10 hyperbolic 0.866 d over h. Okay. Now at top, y is equal to h. So when y is equal to h, what will be the value of this function? Y by h will be 1, so it will be 0. Okay. At the base, when y is 0, y by h is 0, then it will be maximum. Okay. When phi is equal to 0, let us say phi is equal to 90, then what will be the value? Cos phi 0, and when phi is equal to 0, it will be maximum. So when 90, here the pressure is 0. At 0 and 180, it is maximum. So that distribution is coming from cos phi. In the same manner, there is distribution of the pressure on base. Look, the next equation. So there is distribution of the pressure on base. Then there is distribution of pressure on the wall of rectangular water tank. Then there is distribution of the pressure of the convective pressure, and the same distribution is also given in the form of these charts. And the total pressure on the wall you will calculate using the same formula which we have done for shear and moment, 4.10.2. Okay, so equations are available. Only thing is you have to learn how to use it. So tutorial I will give you tomorrow. In tutorial I can ask you either to plot the distribution of the pressure or calculating the overall shear force and bending moment. Both you should know. How to plot the pressure, how to consider gross effort. For considering gross effort, you need to know only MI and MC and their height. You don't need the full distribution. You can calculate the overall effect from it. But if you want to calculate the distribution of the pressure, then you have to use these expressions. And where you will need distribution of the pressure? Where you want to do numerical analysis, like finite element analysis for the actual distribution of the pressure. There you will need this expression. Okay. Last thing before closing, sloshing height. So when this water is shaking, the top portion of the water sloshes, and this is the height of sloshing, D max, the maximum height of sloshing. And this D max, again I am taking from code only. So this is D max is equal to AHC. Of course, it will depend on the convective component R into dy. This is for circular, and this D max is equal to AHC R into L by 2 for rectangular. L is the length of the water tank. What is length? In the direction of water. B is perpendicular to the other. And in case of circular water tank, it is diameter, which is same in both of them. That's all.
What is this R?
R is response reduction factor. Because AHC we have calculated applying response reduction factor. But as we discussed, the displacement does not depend on R. You can only reduce forces, but the displacement will be same. So it is the movement of the water. Movement of water you can't reduce. Whether your structure is elastic or inelastic, it will be same. So whatever reduction we have done in AHC, that we have to nullify by multiplying it by R. Okay, so we will close here. Any question? And when we meet tomorrow, I will tell you chimneys. How to analyze chimneys. And the code we will be using there is IS 1893 part 4. So please be ready with IS 1893 part 4. And I will also give you the tutorial tomorrow, which will consist of questions on water tank and chimney.